Welcome to another video in the series of Mathsy helpful videos. This one, proof by induction, one of the trickier concepts in Year 11 Mathsy, but hopefully this video will go some way to provide an additional opportunity for you to think through some of the structural and really important parts of mathematical proof, but of this type of proof in particular. The focus on this video is not on the mechanics of the algebra of the proof, rather it's on the structure and the importance of the different elements, so that at the end we can genuinely claim it's a proof, not just a random series of showings. Proof by induction is a way of approaching a proof where we, initially at least, completely get away from the idea of showing something is true or showing that a pattern is true by completing a series of calculations over and over and over again. As you can see from this top line of the model we've got here, there is no doubt about it, we could set about trying to prove that something was the case over and over and over. If you think about that, an example of that is when we're looking at the sum of a series of numbers. Maybe it's a sum of odd numbers. We know that it's always sum of two odd numbers is always going to give us an even answer. Now we know that to be true. The problem we have is demonstrating that mathematically. And as I say, over here in this top line of the model, you could just keep on going. The problem is, when do you stop? Well, if you stop, then you haven't proven it to be the case. You've just shown it to be the case for the first 300,000 numbers. So we have a dilemma there in terms of the structure of the approach. So I would say that a series of calculations like that won't get us where we want to go. So let's look at what proof by induction does for us. We have all our proofs lined up, as previously mentioned. And we're going to prove two things. We're going to prove it's true for the first in the series. Okay, very important one. We're not going to prove it for the second, third, and fourth, and fifth, and sixth, etc. We're going to set ourselves up to show that if you approach it and say, if the previous one is true, what about the next one? Okay, so we're going to show that if you assume that the k term or the kth version of the pattern is true, then let's just verify that the k plus 1th, which is the next one, will be true. It then flows naturally that any pair of adjoining observations will be true. Those pair, that pair, that pair. Most importantly is because we've shown that one to be the case there, the first one, what it means is the first one being true and knowing that the next one is true, we have shown it to be the case for the first two. Having shown it to be the case for the second one, we now know it has to be for the third and the fourth and the fifth and the sixth. And you can see that working in this model, there is in fact no limit to how far we go. So we'll talk through this structure in a bit more detail in a moment. Before we get into this proof in particular, just clarify what we mean by proof and draw some distinctions in our language. First of all, Year 9 students are quite capable of calculating a series of values given the process to follow. Showing is a more sophisticated skill. Show that something is true Could be, show that 111 is divisible by 2 or not. Show that the hypotenuse of a 3-4 triangle is 5. The problem is these two here, calculation and showing, don't lend ourselves to a forward-looking proof. They don't lend us to any justification beyond the examples that have been worked through. So why do we bother proving? It's far more rigorous. It's a justification of why all cases must be true. Must be true is a really important scenario here. So in terms of our language, the example we talk about down the bottom here is that let's just add a bunch of numbers together. And what I'm going to tell you is that it's speculated that a series of numbers added up can be described in this form here, n squared plus n all over 2. Now, if we work that out, 1, 2, they all turn out that way. So we carry out calculations and we can justify that this rule stacks up. Okay? And we can just keep adding. So that's again what we talk about with these two dot points. We can keep on adding calculations to it. But here's the thing. A proof allows us an elegant and efficient way to show something is true. We don't need to leave a computer running overnight to come up with 350,000 calculations, still to wonder in the morning whether the 350,001th calculation was going to show something wasn't true. So there's no doubt about it, we've got some new language with these proofs. The axiom of mathematical induction is what we are relying upon. An axiom is when we make a statement or a proposition on which an abstractly defined structure is based. Okay, so the axiom is a proposition. Okay, and the structure is based on this. Now, for the purposes of mathematical induction, we have 3 steps that we're going to focus on. We'll explain these in more detail in a moment, but the first step is to verify the statement is true. For the first case, this first case is a special one. It starts us off. So we have n equals 1 as our first. We're then going to assume in the second step that this generalization, this pattern, is actually true for some point in the series, and we're going to show that it's true then for the one after that. So we're going to have our first in the series, then somewhere down here we're going to prove that those two are proven, assuming the first. And then, by way of the axiom, ultimately at the end, we're going to bring this back and say the first was proven, the second, okay, hasn't been proven, but we have shown that the second is true if the first was. And then we can subsequently work our way forward in pairs if we wanted to arrive at that. So the third step, by induction, since we know that it's true for the first step, okay, it must be true for the second one. It also means then it's going to be true for the third in the same way as we just showed it was true for n equals 2, so the one after that's true. Goes onwards and onwards and onwards without limit. So here's the question. We just did it a moment, or we looked at it. We're showing that series of counting numbers, 1, 2, 3, 4, 5, all the way up to some number n that we don't know, can actually be expressed in terms of this expression. Okay. Now our first step is quite often a trivial one, or appears trivial in terms of our calculations, but it's extremely important. We substitute n into the more complex expression. In this case we get 1. We know that the first term of the expression was 1, so we've got 1 equals 1. Thus this rule that we were wondering about, well, it proves to be the case for n equals 1. That's our first step. So as we continue the proof, this step doesn't require any significant manipulations. What we do though is we insert k into the series and the rule, and critically we are going to assume that it is true. We are stating an assumption. There is no inherent set of calculations here to show that the left hand side is the right hand side or anything like that. We are assuming this is true. We'll move on to step 3. So we're going to continue with the proof that a series of numbers added up equals some fancy rule. In third step, we look at the effect of having a series that now involves a k plus 1th term. Okay. In this instance, we do not just go ahead and substitute k plus 1 into something. No, we add to each side of the expression the value k plus 1. Okay, so on the left hand side, if we were counting 1, 2, 3, 4, we came up with 5, k plus 1 is 6, okay? But we don't put those numbers in, we simply write, as we have written k in the series, we now add plus k plus 1. Having added it to there, to the left hand side, we add the identical expression to the right hand side. Our aim now will be to work with this right hand side, to work with this large expression, to see if we can turn it into something that is of the general form we're looking for in our rule. If we have a look at the blue box, the pattern here is identical to our n squared plus n on 2. The difference being where there is an n, we have a k plus 1. K plus 1, oops, and a typo. That should be a 2 in the denominator. Okay, so we've got an identical pattern, except the difference is we've got k plus 1. Our work is going to be to show that this term here, that has the k squared plus k on 2 plus k plus 1 there, can turn into this. The work we do in the middle of the third step is to try to turn our expression that we've been granted through the addition of the k plus 1, turn that into a new pattern. Of course, the new pattern is only slightly different insofar as instead of having a k in the squaring and the k there, it's got a k plus 1. So the pattern that we're aiming for remains n squared plus n on 2 in a sense. K squared plus k on 2 is where we were at a moment ago. Now we're at k plus 1 squared plus k plus 1. That should be the pattern if we're counting up to k plus 1. We would simply insert k plus 1 in where there was an n. Having said that, is our target. A couple of tricks of the trade. The first is to recognise that we probably need to have a common denominator of 2. So we set about creating that to be the case with a change to the numerator and the denominator. Then we manipulate a couple of terms on the numerator with a view to setting ourselves up with a factorisable quadratic. The reason is we end up wanting a k plus 1 squared. To achieve that, we got a k squared plus 2k plus 1. We've achieved that by rearranging the top terms. So we bounce through here and we have rearranged the terms, which gives us the scope to present a quadratic and then in its factorised form, it's convenient that the residual, the plus k plus 1, just happens to fit the pattern. This work overall then has confirmed the step 3 goal. That is that you can add a k plus 1th term on the end of your summation and express that summation in the formal form or the rule form that we had in mind. So the rule is true for n equals k plus 1. Finally, this brings it home. Very important set of words that cannot be ignored. This is, in essence, the working or the justification that we have a proof. We have to say that because we showed it to be true for n equals 1, and we've shown it to be proven true for n equals k plus 1, given that it was the case for n equals k, the axiom of mathematical induction allows us to claim this as a proof. And again, remembering, it's the idea that we've shown it for the first and for the kth and the k plus 1th. Sorry, we haven't actually shown it for that one there, but we've certainly shown it to be that and shown it to be that. So the question remains, why bother assuming that to be true? Well, if we dial this back to the first and second in our series, not only is the first assumed to be true, but the first is actually true. So if the first is true, and then by this arrangement here, the second one is true, we've shown for the first and the second. Well, if the second is true, so must the third, because we showed a moment ago that if the second was true, or if the kth was true, the k plus 1th was true. So we end up getting the third, and subsequently we can keep going forward. So therein lies that would be the conclusion of your proof, making those comments there, using that language or very similar to it to express the nature of the proof. So by way of recap, just to make sure we're not missing any of the points in the structure of a proof like this, the first step, okay, grounds the proof. It's our n equals 1, and it grounds the proof firmly in the ground. Without this step, the proof of assumed n equals k and shown to be the true n equals k plus 1 are just floating in space. They can't be used to claim the second, the third, the fifth, the sixth, the seventh, because we've actually got no concrete evidence that anything in the first instance has been proven. That is to say, we've assumed n equals k, but that's not satisfactory enough. We need to know that something's true. One is true. Okay. The second step sets us up with a k notation and sets us up with the idea that we're going to be going through to the k plus 1th, and that's what the third does. It's the powerful mathematics that justifies that the pattern runs off into the future. Now the concluding comments can't be ignored. Okay, that is to say, those statements by the proof, by the axiom of mathematical induction, we have shown it to be true for n equals 1, and also shown it to be true for n equals k plus 1, assuming it's true for n equals k. Then by the axiom of mathematical induction, we can bring those comments together and claim victory. Now, two observations at the end. Certainly in my experience, one of the very tricky steps here is the algebraic manipulation of the k plus 1th term. But I would say in almost every case, keeping your eyes on the goal is very important. The goal being, what must the pattern form? What must emerge out of this k plus 1th work is something that is an existing pattern with k plus 1 inserted. And the only other trick I think that's significant is occasionally the setup actually requires you to identify the pattern or clarify the pattern and express it in some mathematical form. And we'll be doing some practice questions on that. Hopefully this video has been helpful. A little bit drags on a bit, it's a complex topic. But hopefully this, in addition to the work we do in class, leave you in good stead. Bye for now.